What makes brittle materials incredibly strong in compression? Imagine smashing a ceramic cup and it shatters into pieces instantly. Yet, that same ceramic can withstand enormous forces pushing down on it without bending or deforming. How is that possible? Well, it all comes down to how these materials handle different types of stress. When you push on a brittle material, like glass or concrete, it resists with a lot of strength. But when you pull or stretch it, it's much more likely to crack or break. That's because their internal structure and failure mechanisms behave differently under compression. Brittle materials are made up of tightly packed atoms arranged in a crystal or granular structure. They don't have the ability to stretch or bend like metals do. Instead, they tend to fracture suddenly when the stress reaches a certain point. Under compression, however, their internal flaws, like tiny cracks or microcracks, tend to close up. This prevents cracks from growing and spreading easily. Think of it like squeezing a sponge. The cracks get pinched shut, making it harder for the material to break apart. This crack closure is a big reason why brittle materials can handle very high compressive stresses. When a load is applied, the internal flaws act as stress concentrators in tension, making it easier for cracks to grow. But under compression, these flaws tend to be pressed together, which actually makes the material stronger. It's like pressing on a brittle piece of chalk. It resists because the cracks are sealed. Failure modes in compression are different from those in tension. Instead of cracking apart gradually, brittle materials often split along specific planes. They can split into columns or develop shear fractures depending on how much lateral pressure they experience. When there's little lateral confinement, cracks tend to form parallel to the load, causing the material to split into sections. When lateral pressure increases, the cracks can turn into shear fractures, which are more like sliding failures. The Poisson effect also plays a part. When you compress a brittle material, it tends to expand slightly in the directions perpendicular to the load. This expansion creates tensile strains that can cause cracks to grow if the stress is high enough. But in most cases, the overall high compressive stress keeps these cracks from opening up. This is why materials like ceramics, concrete, and rocks are used in construction and engineering where crushing forces are common. They're hard, tough under compression, and can support heavy loads without bending or deforming. But it's important to remember that their low tensile strength makes them vulnerable if tensile stresses develop. That's why engineers design structures to minimize tension and maximize compression. In short, brittle materials are incredibly strong in compression because their internal flaws tend to close up under pressure, preventing cracks from spreading. Their failure modes involve splitting or shear fractures, which are different from how they break in tension. This combination of microstructural behavior and mechanical response explains why these materials can support large compressive loads despite being fragile when pulled or bent.